right, so last time we just introduced the concept of a sequence, which essentially is looking at, you can think of it as a function whose domain is just the natural numbers. So we just kind of worked with some terms and the general forms of those last time. All right, now we want to start to talk about and be able to determine, that's what we want to be able to do, is to determine whether or not a sequence converges or not, whether it converges or diverges. So a sequence whose terms are approaching a limiting value is said to converge. If it doesn't have a limiting value, then we say it diverges. So we think about a limiting value, well, we're talking about a sequence of numbers that we're subbing in the naturals. We're subbing in 1, 2, 3, 4, and 5, so on. So we're looking at, based on that, based on the definition of a sequence being the natural numbers, we're talking about that limiting value really as n is getting bigger and bigger and bigger. So as n is going to infinity, as you write out more and more of these terms, are these terms converging or not? Do they have a limiting value or not? That's the same question. Now, there is a more formal definition of the limit of a sequence that really mirrors the formal definition of a limit from Calc 1, which doesn't really get covered consistently anymore. I don't think I've covered it the last couple of semesters. I used to always cover it. If I'm running ahead of schedule, I will cover it, and if not, I typically don't anymore. It kind of got pulled out of AP curriculum, and then slowly it's kind of gotten pulled out of some of our curriculum as well. But here's what that more formal definition would look like with a sequence. Basically says, so here's my sequence in this case. You look at the graph, you see all those little dots here. So let's just kind of talk through this. So what we're looking at is the limit of a sequence. So this is really what we're thinking about, first of all. So let me make a connection here. So a sequence with a limiting value converges. So what I was saying is we're really looking at, is there a limit as n goes to infinity? Is that equal to a real number L? That's really the heart of it. So there will be, that limit is going to exist if for any small epsilon I pick. Like if you look at this sequence of terms, it looks like it has a limiting value. It looks like these terms are getting closer and closer to L. They're bouncing above and below, but it looks like they are getting closer and closer to L. So what this says is no matter how small of an epsilon I pick around L. So in this case, I have picked a very small little epsilon window around L. And so no matter how small of this epsilon window I pick, there will be some value, capital N, which is represented by this vertical dashed line here. There will be some value, capital N, after which all of the A sub n's, so all of the sequence of the terms, or S sub n I think is what we have here, all of the sequence of the terms after that, if we were to find the distance between those terms and the limit, they are going to fall within this epsilon window. So for all of the terms after this value of n, so that after n here, there exists some value, capital N, such that after n, all of the terms of the sequence fall within that little epsilon window, no matter how small of an epsilon you take. So suppose I took an even small, so that capital N would satisfy the criteria here. And what this formal definition is saying is it doesn't matter how small of an epsilon window I take. So suppose I took my epsilon window to be even smaller. So suppose this became epsilon. Buckley, stop. My God, you hear him. His tags, he's itching, sorry. So if we were to look at this as our epsilon window here, so now this is becoming a smaller window around the limit here. So that's where so it kind of looks like actually capital N is still satisfying on that lower part that I just drew. Now though, I'm on the upper window, and do you notice how those first couple of points here up above, those are not falling within my epsilon window. So maybe my capital N for that epsilon, maybe this time it needs to be somewhere over here for capital N, because that last one looked like it was kind of right on the point. And then after that, all of the values in the sequence after that are now within that smaller epsilon window. So no matter how small this little epsilon window you pick around that limit of L, there will be some location, some capital N, such that after that, all of the terms of the sequence are going to fall within that epsilon window. That's kind of the formal definition that says, hey, there's a limiting value. The terms of this sequence are approaching a number. All right, so let's see what we think here. And maybe you just want to go back to the idea of, do you think these terms are approaching a limiting value? Okay, maybe we think about them numerically, maybe we think about them graphically. So let's just kind of think about them here. So on this first sequence, a sub n, I have 1/3 to the n. Well, 1 to any power is going to be 1, so we're going to start with 1 over 3 to the first, and then we're going to have 1 over 3 squared, so it's going to be 1/9, and then we're going to have 1 over 3 cubed, which is 27, and then 1 over 3 to the fourth, which is 81, and so on and so forth. So I would say here, just based on maybe our gut instinct without getting too bogged down in any details yet, it looks like maybe this sequence here is converging to 0. So it looks like a sub n is, these numbers are approaching 0. Maybe if I was to think even in a little more, we'll just do this like one time here. But in a little more specificity, if I started at 1, and let's say I'm up here, so this is going to represent the first value at 1/3, and then obviously not drawn to scale because that's 1, and then when I sub in 2, so if I sub in 2, I'm at 1/9, so maybe I'm right here at 1/9, so this is not drawn to scale, and so on. And then at 3, I'm at 1/27th. And then at 4, I'm at 1 over 81, and so on and so forth. Yeah, it kind of looks like these are, closing in on a value. It looks like the sequence is approaching 0. So we could also think about that graphically. We could also think about, if it looks like that sequence is approaching 0, so I'm thinking that maybe my limit here is going to be 0. That no matter how small of an epsilon window I pick here, so no matter, let's say I pick I'll just even kind of just draw some random epsilon window that's defined by the thickness of my highlighter here around 0. So suppose that this is my just sort of random value of my epsilon window, so this is my value of epsilon. It looks like there is some point here, some capital N, so maybe right around, here is my, let's say, capital N, after which, so maybe this is at 3 or something. This is just kind of a random sketch here, but it looks like everything after that, it looks like all of my data points after that are going to be within that epsilon window. And no matter how small I made that epsilon window, that there would be some value of n after which all those points would fall within that epsilon window. So that's kind of how the formal definition works. Not that we're going to get, too bogged down with that. Maybe right now we just look at the idea numerically, graphically. It looks like this sequence is approaching a limiting value. It looks like it's approaching 0. So I would say yes, it kind of looks like, do I think it converges? Yeah, I think it converges because it looks like it is approaching 0. All right, let's write out the terms of this next sequence. So if I start by subbing in 1, I have this alternating thing, right? So -1 to the first is -1. 6 minus 1 is going to be 5. And if I sub in 2, negative 1 squared is 1, and then 6 plus 1 is going to be 7. And then it's just going to continue to alternate in that way. So 5, 7, 5, 7, and so on. So if I think about this, what I really have is I have this sequence that doesn't look like it's converging into one value. I mean, I might even say it looks like this sequence, I could maybe even write this sequence in a different way here. Looks like my sequence is 5 if my n that I'm subbing in, first term, third term, and so on, if n is odd, and then it looks like it's equal to 7 if n is even. Sometimes you see sequence written out like this. And so in this case, we have what we will call like two subsequences that are converging to two different values. And if that happens, it's not approaching one limiting value. So this one, I would say it looks like it does not converge. So I would say, as we look at this one, we might just say, looks like this sequence does not converge. Doesn't look like it's, approaching a single limiting value in this case. Looks like it's approaching two different values. All right, so as we move into some properties of limits of sequences, they're going to behave in the same way as the properties of limits of functions, because let's think about it. Sequences are just that subset of a function, just focusing on the integer values and the inputs. So the sum of the limit of a sum is the sum of the limits. Same thing with the product, limit of products, product of the limits. Constant multiples can be kind of factored out and carried along, and then the limit of a quotient is the quotient of the limits. That's true in general, and all those things are going to still be true when we're talking about sequences. So now we get into, we were talking in some big generalities before, but we're going to get back to really this main idea of the limiting value. Is this sequence approaching a limiting value? What we're really saying here is, does the limit as n goes to infinity, does that equal some limiting value L? And if so, then that means that sequence converges. So what this theorem is saying is essentially, if you want to think about the limit of that related function, that then the limit of the sequence would be the same thing. So if you have the function defined, let's say for all the positive reals, then if we just focus on the limit of the sequence where the inputs are just the natural numbers, then the limit of the sequence will behave like the limit of the function. All right, so let's just kind of think about if I had a sequence that was n over n plus 1, what would be the limit of that sequence? So the limit of that sequence, well, a lot of ways to think about it. If you wanted to go back to what we've talked about, initially it is infinity over infinity, but that is one of the forms that we are allowed to do L'Hopital's rule. You also could think Calc 1, degree of numerator is equal to degree of denominator, so it's going to be the ratio of the leading coefficients. But in this case, L'Hopital's rule is kind of fun, 1 over 1, and then of course that is simply going to now just equal 1. So that limit is going to go to 1, so that corresponding sequence would converge to 1. All right, let's look at another one. Limit as n goes to infinity of natural log of n over m. So again, we're in an infinity over infinity situation, and I think this is really one where we would, we didn't really have a good maybe Calc 1 way to deal with that, so we're definitely going to use L'Hopital's rule on that. So limit as n goes to infinity of 1 over n over 1. And then as n goes to infinity, 1 over something going to infinity goes to 0. So this sequence, the corresponding sequence that would be represented by natural log of n over n, that would converge to 0. So now we can go back and kind of think about a couple of the opening ones that we were just kind of, this one we wrote out some terms, we looked at the graph. Now we could think about it a little bit more formally, and we could take a look at that limit. So to decide if that sequence converges, let's more formally write out the limit of 1/3 to the nth power. So really what we're focusing on here as n goes to infinity of 1/3 to the n. So 1 to any value n in that numerator is just going to be 1. And so what I have is a denominator that's getting bigger and bigger and bigger. So 1 over a quantity getting larger and going to infinity, that limit is going to go to 0. So just like we kind of observed by looking at it numerically and also looking at it graphically, this limit converges, and it converges to 0. All right, now the second one, well, this limit as n goes to infinity, if you look at the limit as n goes to infinity of -1 to the n plus 6, there's no way to evaluate the limit as n goes to infinity of -1 to the n. It's just alternating, or that limit doesn't exist, I guess I could say, because it's just going 1, -1, 1, -1, 1, -1. So this term right here does not exist. And then I have, plus 6 on that. So this limit is not going to exist. This is not going to converge. Not everything that's alternating, though, isn't going to converge. It's because I have something that doesn't exist plus 6, so that's definitely not going to exist. The other way to kind of think about this one, I sort of like to go back to, and I don't know that this book explicitly states it, but also the notion of how I was writing out when we looked at this one before, that a sub n, if we wrote out the terms, was equal to 5, a subsequence of 5s, if n is, not was, if n is, gosh darn it, is odd. So if we start at odds, we do -1, 6 minus 1 is 5. When we're on the evens, we have -1 to even power is going to be 1, so 6 plus 1 is 7. And so these are what we call subsequences. And so when you have two subsequences, so the subsequence, I'm going to kind of write it out this way. So this, what I'm going to just refer to as this subsequence, would converge to 5. And this subsequence converges to 7. So if you have subsequences that do not converge to the same number, they don't converge to the same value, then we know that the overall sequence then, so this a sub n, does not converge. So I don't know that this book explicitly states it that way, but if you have subsequences that converge to different values, then the sequence does not converge. So that's kind of another way to think about this one. So here we have then some important corollaries here. So if that limit is infinite and then the sequence diverges, so if we were to look at the limit and it goes to infinity, then we would say that the sequence diverges. If the limit doesn't exist, then the theorem relating to, I'm sorry, these are somebody else's notes. Most of the time I've read them through a little bit better. I'm trying to get this last section wrapped up. Then it provides no information. So in this case, so if the limit doesn't exist, so it's not that it necessarily goes to infinity or goes to negative infinity, so kind of like the one that we just did up above. So just because it doesn't exist didn't necessarily mean that the sequence would necessarily, diverge or converge. We really don't have any information if we get to that point where it just doesn't exist. So for example, like an alternating term I kind of mentioned, it, may or may not actually be part of an overall sequence that either, converges or diverges. So it wasn't enough really just to look at the alternating part of that limit. That's sort of why I went on to, I think that kind of gets at the heart of why I went out to kind of write it out in terms of the subsequences, because looking at that alternating factor alone wasn't enough there. So let's go on to talk a little bit more about a different one here that involves an alternating factor where actually this limit would exist. So if we take a look at this one, our negative 1 to the n, and we're being told here to use the squeeze theorem. So of course that is bound in between negative 1 and 1 because it just bounces in between those two values. So now if we divide everything through by n, now remember, if you divide by a negative, you would reverse your inequalities, but here we're talking about, n always being from the set of natural numbers, so n is definitely positive. So we didn't have to reverse those inequalities. So now we have our negative 1 to the n over n sandwich or squeeze in between these other two values. So now we can take the limit of that compound inequality. So the limit as n goes to infinity of negative 1 over n is going to be less than or equal to the limit as n goes to infinity of negative 1 to the n over m is less than or equal to the limit as n goes to infinity of 1 over n. Well, both 1 over n and negative 1 over n, as those denominators increase without bound, the value of 1 over and negative 1 over something going to infinity, those will go to 0. So I now have that the limit that I am trying to find is sandwiched in between zeros. So therefore, this limit would go to 0. So this is kind of the heart of that comment that we were making up above. Technically, if you just tried to evaluate that limit, the limit as n goes to infinity of an alternating factor. So really, if you just focused on, if I was to just focus on this, the limit as n goes to infinity of 1 over n, that doesn't exist. But that doesn't tell me anything about the sequence. So just because that limit didn't exist, I didn't necessarily know about the limit of that alternating factor over n. So this one actually converges. It converges to 0. Whereas if we went back to the one up above here that had an alternating factor, that alternating factor, no, that limit doesn't exist. But that's why I kind of wrote out a little bit further. Let's look at the subsequences and the fact that those are converging to different values. And then that can allow us to conclude in that case that the overall sequence that was given didn't converge. All right, so also kind of summarizing the same fact here. So this must be more how this book writes it out. Divergence can occur if there is no single number that the terms of the sequence approach. So that kind of gets back to my subsequences idea, and that's more like other books' language, that if subsequences converge to two different numbers, then the overall sequence diverges. So for example, and that's kind of what Professor Dieterding summarized here. So this overall sequence, negative 1 to the n plus 6, diverges because the sequence doesn't approach a single number, meaning, going back to what we did, two subsequences approach two different numbers. So that's one way to conclude that that one diverged. And then the easier way to conclude divergence is if we just get infinity, like in the case of n squared. If the limit goes to infinity, then the sequence definitely diverges.